Hi there. In this video, we'll learn about power transmission and how to design shafts that are transmitting power through the interaction of the gears attached to them. Let's illustrate power transmission by looking at only one gear here. And the gear is attached to a shaft. That's the shaft is rotating and delivering a torque T here, which is transmitted to the gear. And this is how power is transmitted. Like you have shafts and gear collectively transferring and transmitting power from one point to the other. But now we're only focused on one shaft and one gear. This shaft has a radius of r, and the torque is transmitted through the gear to another gear through the interaction between the different different teeth of the two gears attached, or kind of interacting. So this interaction between the two gears, or the tooth of each gear together, there's a force pushing. Each tooth is pushing the other one. That force is kind of the translation of the torque from one shaft to the other shaft through the gears. So we're representing that force as F. So this F is the force on the tooth, and with the rotation of the gear and the shaft attached to it, the force kind of rotates, or that interaction of the tooth rotates until this tooth kind of departs. So we're looking at that rotation. And the thing here, the power, we know, like we are concerned about the power here, right? So the power by definition is equal to the work done divided by the time taking to finish or to do this work. Now let's dig deeper into what's work. So work here is defined, so W here is defined as the force times the distance that this force travels. So the force in our system here is not the torque, it's actually the force that's caused by the torque. And this force travels through that kind of arc shape, which is the distance that where the tooth of the gear kind of are in connection or interacting together, and causing that interaction force between them. So the question is, what is F and what's distance here? For a small distance or a small rotation here, this d phi, that small rotation, the arc is equal to excuse me, the radius of the gear times the angle of that rotation. So that's F times R times d phi. I also know that F is the kind of translation of the torque over the radius r, so the torque is equal to a force times the radius, or the distance. In our case here, distance is the radius of the gear. So if I look here, F and R in the formula for the work, I can put them together, lump them together in the form of the torque. So the work is equal to torque times d phi. So looking at the power formula and the work formula, plugging in the work T d phi into the power formula, power is equal now to T times d phi over dt. Now if we look at d phi over dt, so that's something we call omega, or angular velocity. It's how fast that shaft is rotating here. Is the change of the angle of twist, or not the angle of twist, the change of the rotation angle here over time, d phi over dt. And angular velocity is also equal to 2 pi the frequency. So, and the measure of the angular velocity is radians per minute or per second. So what is frequency? F is frequency, and it's measured in revolution per time unit, so for maybe revolution per minute or per second. So it's kind of how many revolutions, how many like full circle does this gear does, and in every circle or revolution you're doing 360 degrees, or in radians it's 2 pi. So going back to angular velocity here, we're measuring radians per minute. It's equal to 2 pi per times f. So now I go back to the formula I have. d phi over dt is equal to 2 pi f. So now my power is equal to 2 pi f t. Very important formula here to remember. So the power transmitted in the gear is equal to 2 pi, the frequency of that power that's generated, and the torque that's transmitted. Or if you are in the strength of materials and dealing with statics and strength of materials, we are interested more in the torque. So torque is equal to P, the power input in the system, divided by 2 pi of frequency of the engine generating that power. And one interesting observation here is that there is an inverse relationship between T and F for the same power value. So for the same power value, if I want to have a higher torque, meaning a higher leverage, I can pull heavier loads, then my frequency will be less. If I want to pull the load fast, so I have to sacrifice how much load I can pull. So I have to reduce T. So if T increases, F decreases. And if F increases, then T has to decrease. So I'm sure, like, depends on your age. Maybe you just started driving with automatic cars, but when you drive with manual cars, you will actually feel that right away. So the first gear is kind of giving you high torque, low speed. So it's just helping you to move because the resistance that you are trying to overcome here is big. It's just moving that multi-ton kind of car, making it roll. So once it rolls, the type of power needed or the torque that's needed to overcome the resistance force and the friction is not that great. So you switch to the second gear. So the second gear will give you a little less torque, but now higher speed. So you increase the speed of the car, and you keep going like until the fifth gear is now you going for speed, man. Like going for speed. So you go for higher speed, and now you don't really have a lot of friction to overcome. Your car is rolling fast. So the fifth gear will give you less torque but high speed. So that's kind of how you can see the power transmission in action and the relationship between the power, torque, and frequency. So one thing to pay attention to, the units for measuring power and frequency. It depends on which system of units you're using here. For standard units, power is measured as in watts, and watt is 1 Newton meter per second. So remember, power is a force divided by the time. The power is equal to the work divided by the time taken. Work is a force times distance, so Newton meter divided by second. Power in the US units is measured by horsepower, and horsepower is equal to 550 pound-foot per second. I can relate watts to horsepower, so 1 horsepower is equal to 745.7 watt. I don't remember all these values, so you would have these for sure handy when you do, hopefully, exam. You have no cheat, or you're doing your professional licensing exam. You will have a huge book to handle or to be your reference. So don't worry about memorizing the values here. One thing maybe you want to try is how they end up with 745.7 as the conversion factor between horsepower and watt. Just look at how to transform from Newton to pound and how to convert from meter to feet. So try this out as well, just to make sure you understand the conversion here of units. Frequency is measured in hertz in the international unit system, and hertz is revolutions per second. And in the US, it's measured in revolutions per minute. So it's just the difference here is 60, which is 60 seconds per minute. Torque, Newton meter, and in the case of US, it's pound feet. Another thing we're going to discuss also in this video is circular shaft design. So we learn about allowable stresses and ultimate stresses. So if you are given an allowable shear stress, which is the main dominant shear stress that's controlling the design of a shaft, and we're dealing here with circular shafts, we're not dealing with like non-circular, so we're limiting ourselves here to circular, which most shafts are circular shafts. So tau max would equal to Tc over J, and this tau max at the outer point of, at the skin of that shaft should be less than tau allow. If we break down J now, pi c to the power 4 over 2, now I can directly calculate the radius of the shaft. So I don't have to do all these steps over and over again because most shafts are circular. So just why not have a generic formula here that if I am giving the torque in the shaft and I'm giving the tau allow for the material, I can size the shaft cross-section right away. So let's see an example here to illustrate the two concepts that we covered so far, power transmission and designing of shafts. So we have here an engine, the 70 horsepower engine with 3200 round per minute frequency. And this engine is connected to the shaft, so that power is transmitted through the shaft to a gear, 3-inch gear, and that gear is lifting a weight W. Question is, what's this, the maximum weight W that can be lifted with this gear that's connected to the shaft and engine shown? Second part of this problem is what should be the diameter of the shaft to be able to transmit that power and the torque? So we're not given a torque, we're given a power and frequency. So we kind of given the torque indirectly through the torque power frequency formula. So I just use the formula, plug in the values for the power and frequency. Power is given to us as horsepower, so bring that to pound-feet units by the 550 conversion value. And then the frequency is given to us round per minute, and because we're dealing with pound-feet second units, so we're dividing over 60. So that will give us 115 pound per minute, feet. That's the torque. Now this torque is helping to lift that weight W, and that weight W is lifted and it's in equilibrium with the torque through that distance, the radius distance here. And if my diameter here is of the gear is 1.5 inches, now I can use the formula for the torque equal to the force times the distance. So the weight now is equal to T over R, and I just plug in the values and figure out my maximum weight that I can lift is 920 if I'm going to use this engine at this frequency, 3200 round per minute. Now if I'm not happy with this weight, I want to use the power to lift a higher weight. So what would you do? You would lower the frequency. So you would, instead of 3200 round per minute, probably would go to 2000 round per minute. And that will give you higher torque. And this higher torque will allow you to lift bigger load. So that's part A. Part B is designing the shaft to be able to resist this torque that I just calculated. So using that generic formula that I spent effort to calculate and formulate, and I can now use it over and over again whenever I need to design a shaft. So C here is the radius, but I'm looking for the diameter, so pay attention to that. Plugging in the values, making sure all the values of the units comply. I'm dealing here with tau allow PSI, pound per square inch, so I need to bring the feet to inches, and that will give me that the radius here is 0.353 inches of the shaft, at least. So I will decide that the shaft will be double, diameter will be double of the radius, and that's the answer here. So in this video, we'll learn about power transmission, the relationship between power P and the torque T and the frequency F. Very interesting formula, and you will see it a lot in action in life in different cases. And we'll also kind of develop a generic formula to help us design shafts, circular shafts, without the need to go over tau max is equal or less than tau allow. We already did that effort, so we can just use the formula right away. All right, that's it. Take care. I'll see you in other videos.